In this video, I am going to show you one other way we have to break up the internal implementation of our module into parts. We have seen that we can use submodules, but submodules leak into the user space. Users of our module have the ability to see how our code is broken up. If you want to hide your implementation details, you can use the partition feature that we have in C++ 20 modules. Again, the idea is the same. We have a math module, but the implementation is broken up into parts that shouldn't be seen by users of our module. So we have a partition, addition is a partition, multiplication is a partition, and these partitions will be imported by the math module, but the way our project is broken up is not going to be visible to the users of our math module. Let's look at some code, and this is going to make it really clear. On top here, we have our math module, which is declared, but this module is made up of two partitions. We have an addition partition and a multiplication partition, and we bring in the partitions by using this syntax you see here. We say import. If you want to use the partition internally in this module file, you can only import it. But if you want it exported for use by people who import the math module, you have to use export import as we are doing here. If you look down, you see our partition. Again, the syntax is what you see here. You say export module and specify the name of the module, colon, the name of the partition, and put a semicolon. This is the syntax you use. After you do this, everything below here is going to be part of this partition, and it can be imported in any other piece of code that is part of this module here. Here, again, we follow the same convention to define the multiplication partition here, and we are importing it. After we have the module and partitions defined, we can import the module, and any partition that has been exported will be available for use in this main function here. This is really something you can do. Now, you may be asking the difference between submodules and partitions like we are doing here. The difference is that code inside the partition can't be directly used on the outside. For example, you can't import a partition like this in the main CPP file. If you do that, you will get a compiler error. But if you want this thing here to be used, you can set it up as a submodule, and you will have the ability to import the submodule if it is what you need. Now that you know this, we can head over to our IDE and play with this a little more. Okay, here we are in our Microsoft Visual Studio IDE. The project is 4810 module interface partitions. We are talking about module interface partitions because there also are module implementation partitions that I want to go to in this chapter because compiler support isn't good enough across all compilers that we are interested in, but that's an idea you can look up. Let's hop over to the repository and see the files that make up our project here. We have an add partition interface file. We have a multiplication partition interface file, we have a math interface file, and we have the main CPP file, which is going to put everything together. Below, we have the compilation steps we have to follow with Visual C++. This is what we are about to do. But for G++, notice that we also have a bunch of instructions here that you can follow. For Clang, again, because we are using partitions, there is a special naming convention that we have to follow. If we are setting up a partition for the math module, we have to name our PCM exactly this way. You have to put in the name of the module, dash, and specify the name of the partition, and then say .pcm as we are doing here. If we go back to our interface file, we will see that the name of the module is math, and the partitions are respectively named addition and multiplication. And you should be able to map this to our naming convention that we are using here for Clang. If you ignore this, this is going to bite you and waste a lot of your time if you care about the Clang compiler. Let's hop over and create these files in the IDE. So the first thing is going to be, let's go back again and make sure. Math, add partition, multi-partition. So this is all we need. Let's create the math interface file, add, new item. It's going to be an interface file. So math, The second one is going to be add partition. Let's check again because my memory is not that good. Add partition, multi-partition. We need to add these files here. So add underscore partition, and we have to add mult underscore partition. Let's do that. Partition. And now that we have the files, we can put in the content. Let's go back to our repository, copy the code for our module file. Let's come back and put that in math.ixx. We paste in here. We can go back and grab add partition and copy the code and put that in add partition in our project here. So let's remove and paste. We need to grab the multi-partition file. Again, it is just going to be defining the multiplication function here. Let's copy row. This is going to copy the file, and we can close this and come back to our IDE, multi-partition A, and put in everything. Now we have all the code we need. We still need to set up the main file though. So let's go there, main.cpp, and put in the code. And we can paste the new content in here. Now that we have all the content, we have to make sure to enable C++ 20 modules. Don't forget that. Otherwise, you will have a lot of problems. So enable C++ 20 and go back and enable scan sources for module dependencies. We need to set this to yes. Apply, okay. And now if we build, let's rebuild solution. It is going to scan for module dependencies. After that, it is going to compile. And notice the order here. We compile the partitions, then we compile IO stream, then we compile the interface file, then we compile the main CPP file. This is the order that this Visual C++ compiler is using. And if we debug and start without debugging, this is going to give you the output that you expect. Again, we are talking about module interface partitions. Partitions are good if you want the main interface file to be broken up into internal parts, if I can say it like that. But the way your thing is broken up shouldn't be leaked to users who import your module. For example, importers of math here don't have an idea that we are even using partitions inside our module. This is something internal to our implementation. And we can use this technique, for example, if our module is being developed by multiple people. One person may be working on the addition partition, the other person may be working on the multiplication partition, and we can put everything together and make it available for users of our module as we are doing here. Okay, we have used the Visual C++ compiler, but we should also use the other compilers as we have established in this chapter. So if you want G++, these are the commands. If you want Clang, these are the commands. If you want to use the Clang that is embedded in our Docker container, or if you have Clang 18 installed in any other way on Linux, you can use it like we are doing here. I have to say that this is the last video in which I will be showing all the compilation steps, but I will be providing this README file that you can read to see instructions on how to compile the files in this project here. But this is the last video in which I saw it live for Clang and GCC because this is time consuming, and I really think you have got the hang of it because we have done this multiple times. Now let's see how to do this with Clang. So let's grab the command. Okay, so the focus now is to do it with GCC. These are the commands. So let's grab the first one here, copy, and go back to our terminal. We will be using PowerShell here. Let's do ls to see the files. Again, you see the files that make up our project. You can see them right here. So we need to compile the header unit IO stream, put in the command. This is going to work. Let's grab the command to compile the partition. We paste that in here and we hit enter. Let's grab the command to compile the other partition. This is the command you can use. Go back to the IDE and put it in. And we need to grab the command to compile our module, which is going to be bringing in the partitions. So let's go back to the IDE and paste this in. And if we go back, the last command is to put together everything and create our rooster binary. Let's go back to the IDE and put this in. And by now, if we do ls and hit enter, we should have our rooster binary generated, and we can run it by saying rooster, and it is going to do whatever it is supposed to do in the main file here. Next, we are going to see how to use command prompt with Clang 16. But before we do that, let's clear our mess. So we should remove any PCM files, remove any object files, and remove the rooster binary. Now we should be clean again, except for the noise that comes from Visual C++, but we are going to ignore this because we need the good editing features from this IDE. Let's go to command prompt and go to the Clang compiler in our instructions. And the first thing is to compile the header unit. So let's put the command in place. This is going to go through. We can compile the first partition. Notice the naming convention again. I am going to repeat this. You have to say the name of the module dash and the name of the partition. If you don't name things this way, you will have errors. You have been warned. Grab this command, put it in here, hit enter. It is going to go through. Grab the second command to compile the other partition, copy, come back to our IDE and paste in, hit enter. And we need to come back and grab the command to compile the PCM file for the module. We can come back here and paste. This is going to do what we want. Let's come back and grab the command to compile the main object file. Grab it, come back to the terminal, paste, and hit enter. Let's go back and compile our object files. The first partition is what we need here. Let's come back to the IDE and paste and hit enter. We need to do the same for the second partition. Generate the object file for it. Let's come back here and paste and hit enter. And we need to compile the module into object code format. So let's do that. Paste, hit enter. And we need to come and grab the command to put everything together. And if we do that, this is going to generate our rooster binary. dir is going to show us the content, and we can sure see the rooster executable here. If we run it, it is going to do whatever it is supposed to do. And we have successfully compiled our code that uses partitions using the Clang compiler on Windows. The next step is to compile with the Clang compiler living inside our Docker container. Again, if you find this confusing or for whatever reason you don't want to do this, you can safely skip this because it is just another option to compile your code. I just thought I could show you how to get access to the latest compiler from Clang if you need that. And Docker is a good way to do that. Let's clean up the mess that was left in by the Clang compiler on Windows. Remove any object files, remove any PCM files, and remove rooster. This is going to clean everything, and we can see that we have the initial files here. We still have the GCM cache folder from GCC. We can remove it as well. GCM, and it is going to go away. Now we should be clean. Let's do lsalh to confirm, and we have our initial files here. Let's go back and compile using the Clang compiler on Linux. Copy the command to compile the header unit iostream. It is compiled. Let's go back and grab the command to compile the first partition, and we will put that back in here. Hit enter. Notice the naming convention again. I really want this to be super clear. The PCM files for your partitions should be named exactly like this. Say the name of the module, put in a dash, say the name of the partition, and then .pcm. If you name them in any other way, you will have problems. You have been warned. Let's grab the command to compile the other partition. So let's copy and put this in place. The command is here, hit enter. It is going to be compiled. We need to compile the PCM file for our module file. So let's do that. And we need to grab the other command, which is going to generate the object file for our main file. So let's grab that and put that in place. The next command is going to be generating object files. The first one is for the addition partition. We grab that and we put that in place and hit enter. It is going to go through, grab the other command, copy, and bring that inside our terminal here, put it in. It is going to go through, and we want to grab the other one to compile our math PCM file into an object file. So grab that, and we need to grab the last command, which is going to put everything together. Grab that, put that in the IDE terminal, hit enter, and if you do ls, you will see everything, including the rooster binary that we just generated with Clang 18 on our Linux container here. Let's run the program. It should do whatever it is supposed to do. This is all I had to share in this lecture. I hope you found it interesting. I am stopping here in this one, and I will see you next time.